Now, time series is another type of data that we should look at. And again, we don't have time to go through in detail, but I think it's worth mentioning here because it's a really important application. Starting from medical data, that things are becoming time series, or even simpler, temperature data. All right? And think about the application of measuring temperature every 10 minutes, every day for 1 year. What happens? You are collecting numbers, right? Every 10 minutes, you are collecting degrees of Celsius. Not only this, you can collect even more data from the sensors that you have actually located within a room, within an area. You can get atmospheric pressure, you can get humidity level, you can get air index, quality of air, and so on and so forth. All of those entities, quantities, they can be used as features for your temperature prediction, for your, what we call it, forecasting. Okay? And the idea here is that you will get a sequence of temperatures, and you should be able to find a way to predict the temperature 24 hours from now. That is the task. That is what we are seeing here. That is what we have also in one of the labs that you can do at your own time. Okay? So we have a collection of temperatures again, and I'm asking to you, using this in order to predict the temperature 24 hours from today. Right now it's 11:25, the temperature is 29 degrees of Celsius. What is going to be the temperature tomorrow at 11:25? Good? Is it clear, the question I'm asking? Okay, that's what we're gonna see. But before we see how to do it, we need to really see the data overall. So here in this slide, you see that we have a two-dimensional plot figure where in the x-axis you have time, and that's why we call it time series. And time there is measured in intervals, 10-minute interval. And on the y-axis, you see the range of the temperature from -20 Celsius to 40 Celsius. You see that as we are moving across the x-axis, so as time evolves, we see that time actually follows, we see that temperature follows a periodic cycle. Okay? That is actually really important to observe before you even start modeling. You need to actually see that any quantity that you are trying to predict follows a particular trend. And I'll tell you why. Or you can tell me why. Or I'll give you a hint before you tell me why. Do you really need deep neural networks to predict the temperature? Say that you want to predict the temperature tomorrow in Albania. Do you really need deep learning for that?
No.
No. Today is 29, so tomorrow it will be 29. Is it safe to say?
Most probably, yes.
Most probably, yes. So, and this is the point. The point of the lab, you will see that when you are trying to make a prediction, you need the baseline. The baseline is actually how to compare against. So if you model later on an RNN or something else, you need to actually know that what you are getting is good enough. Okay? And now we do not have a classification problem anymore. This is a regression problem. And what you're going to output is just a single number. It's 29.3. How would you know that 29.3 will be something valid? Or how do you know if your architecture is doing something correct? You don't know until you have a baseline. And the baseline is actually what we just said. Tomorrow, 11:25, it's going to be 29.3. Okay? You will see in the lab that this actually gives you a mean absolute error of plus or minus 2 degrees of Celsius. Just guessing. All right? Now, in the lab, you will also see that doing any type of architecture, basic traditional neural networks, CNNs, it will completely fail this task to even reach this guess that you have made. So you will use a CNN to predict temperature, it's gonna fail badly. And I can give you even the numbers. I think it's like you will be off by 10 degrees of Celsius if you use a CNN to predict the temperature tomorrow. Right? If you use a basic traditional neural network, it's gonna be like 17 degrees of Celsius off. Right? Why is that though? I mean, this slide is irrelevant, I'm gonna explain it again. But why is this? So our brain, when we are making a guess, what does it incorporate? We are making a guess and we say tomorrow it's gonna be 29.3, as today. But what are we having in our mind when we are making this decision?
Time of the year, the yesterday.
Exactly. The time of the year plus the temperature of today, the temperature of yesterday, the temperature of the day before, the day before, the day before, up to, let's say, 5 days. Okay? This order of temperatures matters in the final decision. So far, with all the architectures that we have seen before today, we have seen traditional neural networks and CNNs. Did we ever take this order into account? No. We never actually seen historical data before in order to make a decision for tomorrow, right? So we took spatial information into account because we used images, or then we saw each pixel independently, which is great for other tasks, but not for temperature. All right? RNNs, now you know, or you all know, that memory is the important thing. Okay? So, the only thing that we need to keep in mind before we start doing the lab, or you will do the lab at a different time, is actually how to prepare the data. Unfortunately, with forecasting, you have to do a lot of work preparing the data. It's not just like text, that you take the text, you come up with vector representations, embeddings, you give it to the network learns and makes decisions. You need to actually find sophisticated way to split these long sequences over 1 year into very sophisticated windows, okay, that could be fed into a neural network, into an RNN. All right? And this is actually what we have on the right plot. So the time there on the horizontal axis is actually the time for 1 year, for 1 month. Okay? But in order for the RNN to work properly and training to go smoothly, you have to actually create a window that will slide across that time. And every time it slides, it extracts several values. These are the values of the temperature for, let's say, 5 days. And sliding actually will create those sequences. Now, are we ready? Yes, we are. Because we do have sequences that can go into the neural network. Yes? All right. Something else that we need in order to make the neural network work properly, we do. It's not only temperature about. The neural network will become more sophisticated if we include other measurements from the sensors, like humidity, like atmospheric pressure, like air pollution, and so on. These, the rest of them, will act as features for your forecasting, for predicting temperature. Okay? And eventually, what you're going to end up having are those embedding matrices, but we don't call them embedding matrices anymore. We call them just matrices with all the data, but in a sliding fashion. Yeah? Okay, good. This is actually the mean absolute error that you will see in the lab as well, if you just run the baseline model, making the prediction yourself. You will be off by 2.56 degrees of Celsius if you just make a guess that tomorrow it's going to be like 29.7. right? So now, in the lab, you will see that you have to find the right architecture to beat this number, or to be as close as possible to this number. And the first two architectures that you will see in the lab, which are the basic traditional neural network and the CNN, both fail to be even close to that number. And that is actually the summary. So we are actually doing a little bit of comparison, and that's again in your lab. We have different RNN models, okay, and we saw that the winner is something we call the stacked GRU. Remember, the GRU architecture is the one that is the simpler version of LSTM, right? And what is my point out of this slide here? The point is that you don't really need the more complex architecture to make predictions for that task. You don't really need to incorporate very long memory in order to predict that task. And see what happens. When we use a simple LSTM, okay, like what we do with text, we end up not only doing a bad job in the MAA, but we are ending up with overfitting. When does overfitting happen? When we are introducing a lot of parameters in the model has to train a lot, and then it does very well with the training data, but it fails to generalize with the testing data. And again, LSTM will work in the training phase, but it will fail with the testing. However, the simpler model, which is the GRU, which doesn't actually incorporate this very long memory and so on, will be the winner. Good? Okay. Let me see what else I have. Nothing else in these slides. I would like to hear your questions if you have. We go fast with this because we would like to do other activities. But I wanted to show forecasting because I think it's an important application. Okay? In the Google Classroom, you have a lab again, which is about forecasting for this data set. And you will be able to rerun the whole notebook in your Google Colab environment pretty efficient. Okay? And we have also comments on each line of code, so you will see everything there. You can do it.
Before
Yes.
starting the lab, so it would be good if you spend 10 minutes to do the quiz. We discuss the quiz, and after that we'll start to talk about the lab.
Yes, and we have also one more activity, which is the project. So we're going to start dates, day 3.
Yeah.
Time runs, so we have to start the project, okay? Or discuss the project at some point.
Please spend 10 minutes in doing the quiz first.
I still don't have internet.
Yeah.
I don't have internet and
Oh, you don't have
it was
internet?
interrupted.
Let me see if I have internet. Because if I have internet, what we can do...
I can't see your network anymore.
Yeah. And let me start my notebook. internet? Okay. I mean, that's fine. Someone is working 24/7, fix the internet. Did you fix it? Okay. But we can go through this together. How is virus works? It's safe to one, yeah. Oh, so you see that at that point, what really matters, the basics, right? Have internet. So if we don't have internet, it's like we don't have water, so life cannot continue. So we don't have internet, life cannot continue. Thumbs up, life will continue. Okay, good. Yeah. I'm still using a hotspot from someone kind who shared the hotspot with me. Then we're gonna heal the hotspot. Oh, you good? I don't know about it. But I think we can go through this quickly. So what is the main advantage of an RNN compared to a standard feed-forward network, to a standard neural network that you know? Okay, very good. So it maintains context across time steps. Yes? So the time steps, if you use time series, it's very clear what it means. If you use, let's say, text, it's also, you know, sequential, so you go from one token to another, all right? The next one, standard, dense, and convolutional 2D networks flatten time and may destroy temporal context. True. Very good. So, basic neural networks, nothing into account. No spatial, no temporal. CNNs, spatial, RNNs, temporal. Okay? In the recurrent update equation, what's the role of state equal output underscore T? Very good. What is the vanishing exploit or vanishing problem in RNNs?
Too small, overlaps.
Too small, right? Vanishing. Exploding too big. Alright? Which component of an LSTM is primarily responsible for deciding what information should be discarded? Forget? Forget. Very good. So, and by its name, right? By its name you can find out. Again, LSTMs we haven't covered in depth, but you have all the ingredients to do it yourself now, right? Even using an LLM, you can, if you hit those popular terms there, they can tell you in one sentence what each of these is. And you can even educate yourself by creating like a small data set, right? 4 sentences. Each sentence is an observation, and ask, what is the forget gate, what is this, what is that, right? Why is normalization important in time series forecasting? Okay, that is actually coming from no matter what, right? If we do time series, if we do something else, if we do pixels, we normalize because there are differences in different features that we don't want to highlight across training. We don't want to be magnified across training. So we want them all to be at the same scale, all right?
Otherwise you cannot compare.
Right. Why can dense networks and 1D convolutional networks sometimes perform poorly on sequencing? Yeah. So intuitively, this is the second one because we said that again and again and again every day that we don't have the chronological order in the other cases, right? But something here is new. Do you see that on nets 1D? So far you have seen 2D. Two-dimensional convolutional neural networks versus one-dimensional convolutional neural networks. What does this mean? It means that CNNs can be also used in text. If you just go back yesterday, you will see that we have an image and then we are defining a convolution like a filter applied to an image. The filter is also two-dimensional and we are scanning across all pixels and we are coming up with values. All right? Now, in the 1D case, one-dimensional case, it's exactly the same, but instead of having a filter that is two-dimensional, it's one-dimensional, it's a vector. And what happens? You have a sentence, we take this filter, and we just slide it to the right. All right? But still, we are missing this temporal information from there. We are getting spatial information, so now we know how the word next to me influences me, but there is no memory in that. Okay? Why does recurrent dropout work better than standard dropout in recurrent networks? Okay, this is actually, we haven't covered it. So you say third one, it's correct. The third one is the correct one. But shall we start from dropout first?
Yes, because
because we haven't ever explained dropout. So, you remember that when we are dealing with a lot of parameters, many parameters, one of the dangers is overfitting, right? And when we have overfitting, that means we have to do something to get rid of the overfitting. The early stopping that we explored yesterday, which is actually get the learning curves and check where to stop, is fine, but it doesn't solve the issue of overfitting. Okay? So there are other mechanisms that can help you avoid overfitting. One of those mechanisms is something called dropout. Remember, in a traditional neural network, you have all of those weights that we need to learn, okay? And there are the neurons within the layers, right? So, with what happens with dropout? If we include dropout as one of the layers, then while training, while feed forward and backward propagation happens, and gradient descent happens, some of the neurons become inactive.
Weight is zero.
Huh?
Weight is zero.
The weight is zero. What happens in this case? In this case, immediately when some neurons are inactive, that means that we are trying to train less parameters. Okay? And that is actually helping with overfitting because we are reducing the complexity. But what is the special thing about dropout? It's not only that it's making inactive a couple of neurons while training. It is actually, training is an iterative process. It happens for every iteration, every step, when we are getting data, new data, right? So the dropout randomly picks a percentage of the neurons at every iteration and make them inactive. And at the next iteration, a couple of the previous inactive could become active, and others will become inactive. Okay, so imagine, I'm going to make this analogy. Imagine that we are in this room, right? All of us. We are neurons. Okay, and we are trying to actually make a decision or try to solve a task. The task is make coffee. Yeah? And there is a training process for that. So if I include dropout, that means that the day one that we start learning how to make coffee, a couple of you will be inactive. The next day, some of you will be active and learn how to make coffee, while we already learned how to make coffee will be inactive. And that will continue. Okay? This is the same analogy as working within an organization when people take days off. When people take days off, does it mean that the project gets killed? No, right? The project will continue, needs to be executed. And also that doesn't mean that the people who are taking days off, they do not know about the project eventually. They get in, some other people get out, and whoever gets in learns about the project and so on, right? That is actually the role of dropout. And why is that? Just because we want to avoid this over-communication. Because if we all stay in, there is no real benefit learning how to make code. Good? Say that again.
We add it when the compression is higher, not throughout the network.
We are adding this when we have a lot of parameters, and we usually add it when we see that the network is getting overloaded, and most of the times we do it at the end, at the bottom. So you see the dropout is actually one line of code that you are adding after a layer. Good?
Just to clarify, is a new layer, let's say, similar to different layers that we have been looking. We have been looking at convolutional, max pooling yesterday, flattened layer, dense layer. So this is another layer that we had in our
It is adding a probability value that certain percentage of neurons will become inactive, or some weights will become zero.
So you say 0.5, for example, 50% of the neurons during the backpropagation process, they will not be active, so their weight will be equal to 0. So that means that they will not be active.
Great. Okay, so other ways of getting rid of overfitting could be something called regularization. If you have worked with linear regression models, regularization is something that you are adding to the cost function at the end. It's like a lambda times the norm of the parameters. This is actually, you are regularizing the model, and you are forcing the model, or most of the parameters, to go towards 0. Okay? So popular models for that, for instance, are ridge regression or lasso. Okay? In the lasso, you are forcing many of the parameters that you are learning, like the weights, to become exactly 0. This is actually reducing the complexity of your regression model. Many of the parameters become 0, and then you may be able to generalize better. Okay? And at the end, also you can do variable selection using this. Why must the return sequence is equal true be used in the first GRU layer when stacking recurrent layers? This is again something that we haven't covered. To pass the full sequence output to the next recurrent layer. Okay? I mean, intuitively, this is what it should do. Okay, and last one, which I really like. Why are bidirectional RNNs often inappropriate for weather forecasting tasks? I will start with what bidirectional means. Bidirectional is when you have a sequence, let's say text, right? You are saying that I want to start from one side and go to the other side and incorporate memory. Okay? But what about we go the other way around as well? That will help even the network learn more about the different structure and context within a sentence. So, however, would bidirectional, will this idea be appropriate for weather? No. Why is that? Weather goes by time, right? So we should go only one direction. We never should go back. We use historical data to predict the future. Never use future to predict history. Good? Good. That's all.
Unless we find time machine.
Yeah. Unless we, yeah. Maybe that's the next project.
Who knows?
Okay? Questions? Not much, that's good. So again, there are two more activities for today. So one is the lab.
There is a question.
There is a question, and we'll go to the question. Yes?
That's for the dropout. How is like 50% dropout? That's some recommended value, or does it?
Technically, you want to do like 0.2, 0.3. We added 0.5, that's fine. technically speaking, this is a parameter that you tune eventually. So the 0.5, 0.3.
Yeah, because 2.5 seems a little bit romantic.
Yeah.
For smaller data.
Yeah. So 0.5 means actually 50% will be inactive, randomly picked, which is a little bit too much. So let's do the 0.2 perhaps. Okay, so the lab for today will be sentiment analysis. And what we are going to do is we will load the popular data set. Do you wanna go through this? We are gonna load the popular data set. It's a reduced data set that is within Keras. Okay, we're gonna make a split in the cheap way. And what we are going to do is we will train a model to make a decision whether a review of a movie is positive or negative, whether the sentiment is positive or negative. Okay, so this is a binary classification problem, the same way you have seen so far binary classification problems. The difference here is that we are using text as input data, and we have to, fortunately, use RNNs, like what Gerta explained at the beginning. All right? Questions? So, we're going to introduce loading in a cheap way the text data set, converting the numbers, converting the words into the numbers, padding the sequences, what you saw. Some of the reviews could be long, some of them could be short, but we require all of the reviews to have the same length. Okay, so padding will be there. Building the embedding layer, which is one line of code, by the way. So embeddings means I want the movies, I want the reviews to become numbers. Training the RNN LSTM model, evaluate and visualize the learning curves. Good? Okay, so the first part is just importing the library, nothing special. We have seen this again and again every day. We are checking for GPU, which again, no need to talk about. And the first thing is load the dataset. And fortunately, the dataset is preloaded somewhere. Yes.
A technical question. Should we make a copy of this lab in our Google Drive or work directly with...
You can download it.
Okay. Yeah. Okay.
So you want to download this? What's your question? Or maybe
are we going to modify to experiment with it? I think so. So should we download it or?
Yeah, download it. Yeah. I mean, you don't have to do it right now. You can do it home, but
The question is that if we just open that copy, we cannot modify it. But if we make a copy, it is possible to modify it.
Yeah.
You download it, you open Google Colab, you upload your notebook, and after that you can modify it and rerun it many times, as many times as you want.
I have already run it, and we can display right now what the output is. But you can do it even now, or home, or later, or in a month. Okay, doesn't really matter. So some parts of this lab could be used also for your project, because your project is about text. Right? So feel free to copy paste parts from there for your lab. Feel free to actually copy paste what I'm gonna give to you today, tomorrow, the day after in your project. Use code from ChatGPT, Claude, whatever you are using, okay? But make sure that you understand what's going on. That's the bottom line, okay? So, someone talked about vocabulary. I don't remember who, but you did. No, okay, someone else did. Important. When we load the data, remember, these are reviews. We can say whatever we want in the reviews. There is a vocabulary. These are the number of unique words that you can identify within this corpus. All right? So one thing that we need to do is not work with all single words. It's too much. So what we can do is we can restrict the vocabulary. What do you mean to main thing?
For example, we are working on vocabulary about medicine. We will be using only words that are related.
No. you do not cherry pick the words now. What you do is you are saying that if the vocabulary size is, let's say, 1 million words, I'm gonna pick only 10% of that. And then it will actually go and find 10%, the corresponding 10%. Okay? So you want to cherry pick? Yes. There is a function that does. Yeah. So you specify the number over there, okay? And then you load the train and test data along with their labels using the Keras dataset IMDb dataset. The Keras function IMDb dataset. Okay? And you specify now the number of words here, which is like 10,000. Okay? Now, within that function, they're gonna pick the right 10,000 words that need to be picked in order to move forward. Okay? So we display the number of training reviews and testing reviews. So we picked 25,000 and 25,000.
Is this the dimension of the matrix?
Yeah. Oh, what is the dimension of the matrix? Yeah, I think it's coming here. Sure. So here we just print the length of the training data, right? And it's like 25,000, okay? I may pick a little bit too much for the testing. It doesn't really have to be that much, but that's fine. Or I may pick a little bit too small. No, actually, no, this is the 25,000. I think that's the
They are coming
maximum.
automatically. You have not.
Yeah.
This
Yeah.
is what it
This is the default, right?
It's default.
Okay.
This is what it exists.
Yeah.
And that I was wondering now why they have this data set the same number of training and testing, because usually we use more records for training and less than for testing, but maybe due to the fact of being textual data, let's say.
Could
because
be.
yeah,
Yeah.
this is by default coming 25,000. We are not splitting or selecting.
Yeah, this is actually exactly that came out from the
Yeah.
function.
No.
And here is actually one thing. You see that I am a little. I see that, and now I'm wondering why. Yeah, because when I was preparing this, that was in a rush. I know this function that loads data. It does it, and it comes out. But I never questioned myself why. But now it's the time to question ourselves why. Which is fine. Also, this is like a Keras thing. It's a TensorFlow thing, okay? So what I would do to answer this question is I would go to the documentation of TensorFlow and Keras for this dataset, which is pretty easy to find, by the way. If you Google IMDb Keras TensorFlow, you will actually get a full description of this dataset, and you will even see examples how to do machine learning with this dataset. Good? Yes?
Just a summary. If you can go very briefly, what does this command do? Yes, the one we were just discussing.
The load data.
Yeah,
The
the
load.
load data. Yes, Keras dot datasets dot im.
From this
dot
object,
load.
the datasets,
Yes.
what you do is there is a function, or not, for the object, from the object IMDb, what you do is you are calling the load function,
Which loads the data.
which loads the data, which goes to the server, I may use the right words here,
Okay.
and loads the dataset, the IMDb dataset, which is,
There are 4 data sets there that we are just loading, nothing. We are not touching at all, just loading.
yeah, just loading, just getting the data into the memory of our system, either the Google Colab or my local machine, okay?
And this
And the
param-
length of the data, it means the total number of sentences that we have. Okay? So this is the length function,
and
what
the-
is returned.
And the number of num words is the number of words that.
The number of words means that how many tokens or words would you like to have in all of your reviews.
Okay.
Okay. The one example from there, the movie was unbelievably spectacular. Okay, we already know the positive the sentiment of it, but there is a underlying mechanism in the code that you need to tokenize, right? And what you actually do is that each word has a particular ID. Okay? And this is actually the ID that's going to be mapped on that array. So if you just read this array, it's 1, 17, 13, 24, 56, 7,821. Okay? So these are just the IDs of each of those words. Alright? This is how we're gonna store it. Okay? This is actually called tokenization. Each word receives an ID. And this is the starting point with NLP.
It's like a pointer, let's say.
Yes. It's more of a programming thing rather than a mathematical thing, but this is how we start, right? So each entity receives an ID. And with this ID, we're going to start now making embeddings, countings, whatever we desire to do, all right? But this word will carry over this ID until the end. It won't change. Good?
The larger the number, the more important the word is. The larger the number, the more important.
No, no,
It's
no.
not about importance.
This is just ID. Like we are in this room, all of us are words. It happens that I am the first word, I'm receiving a 1. Ogerta is receiving a 2. Doesn't mean that I'm more important than Ogerta.
We are
okay?
not processing at all.
Yes, it's just IDs.
It's a mapping, let's say.
Yeah. And for computational reasons also, the mapping is important. Okay? So now we pre-selected 10,000, and that actually means that if a word is too rare and not in the top 10,000, that means it's going to receive something U and K, unknown. Okay? We just got it out of the vocabulary. Good? So this is actually the first exploration that we do with the data. So we just pick the first review from our training data set. And we also specify that we want to go 50 tokens, up to 50 tokens, right? And we know that it's going to be stored as a sequence of numbers, but each number is an ID. And that's what you are seeing over there. You do not really see the real review, but what you are seeing is the IDs of that review, okay? And the label. Now, later on, because I don't like to see only the numbers, because I don't really mean what they mean. Yes?
So would it be better to work with linked list or with vectors?
To work better with
Linked list. Linked list?
or with vectors.
Yeah, for the data.
But for what? For what? For modeling?
Yeah.
For modeling, this is, yes, with those will become embeddings eventually. This is actually the way to work. I don't know if I answered your question because I'm not sure I understood your question correctly.
So in programming we have like the vector and the linked list.
This is Python. The list is maybe a linked list. It can be whatever, but it is a list. It is a
This is
Python
the
list.
list. I mean, when I call a vector, okay, good point. Now I understand. When I call it a vector, it's a list, by the way.
Yeah.
So there are two ways of saying the same thing. From a programming point of view, it's a list, or a structure, or something else, or a variable. In mathematics and data science, when we say a vector, it's the same thing. It's like a brackets, numbers. So it's a list.
List is data structure.
Right. But in mathematics, there is an additional thing that we are adding, that the vector lives in a dimensional space, and you can even draw it. Right? It's like something, like an array.
Just for the number, for example, someone right get why the numbers are different. If we explain like in the linked list, it will be easier to understand why the numbers like are not 1, 2, 3, 4, 5.
Yeah.
And are 1, 14, 22,
Yeah.
26, and so on.
Yeah. I mean, and that's correct. So for those who are more familiar with programming, when we say list and ID, they know why this is happening. Okay, 1, 14, 22, 16, and so on. Good? But again, we have a diverse crowd, so I don't want to favor one field rather than. So you know what it is, so keep it. Good? Something important. When I decode the review back to words, So actually, I'm going to the mapping. I'm using your language. I'm taking the mapping and I'm going to one to the word, right? You can go vice versa. The one goes to there, the word there. Okay, that's the idea. So I can decode it back. So if I have the one, I know that is the word there from that list. So I can get back the full review in words now, and I can see what it is about. So I can read it. And you see that I'm using something called dictionaries?
Yeah.
I know a little bit of programming.
There is a key value pair. Yeah.
Yes.
No.
Dictionaries is very important when you are doing programming. You know better than me because you are engineers, computer scientists. I'm not. But I know that dictionaries are very powerful to store data.
The key is
And you have the key and the values. So you can go back and forth, and you can even use dictionaries to, yes, and even do other things, okay? Even do machine learning with just the dictionaries. So here we have that, and I'm accessing it within a for loop inside, and joining all the different words together. There is a function join. Do you see that? There is a white space. I hate doing this. I don't know why. I don't like talking computer science. So I'm sorry. No offense, okay? No offense. But there is a white space here. Now, all the tokens, they are not joined together, right? They are here and there. So what we actually do is we identify the white space of that, and then we join them together using this function.
like the concatenation of the things.
Yeah, concatenating strings.
So when you read it, you see actually the question mark. Do you see that there is a question mark? Yeah. What is the question mark?
A word that is not in the dictionary.
But there is a question mark here too.
Yeah, but we are using it
The missing word, right? So there is one word that doesn't appear in the vocabulary. I pre-specified the vocabulary to be 10,000 words. So it's not going to be there. Something is missing. Someone talked about missing text, missing tokens. Does it really matter here in this task? No, it doesn't really matter. You can still understand the sentiment with even reading that without the full list of tokens. Even if I remove more, you will be able to get the sentiment. The machine can do as well. All right? Okay. Now, the length, Ogerta mentioned that the length of each sequence is not the same. So what we need to do is pattern with zeros. So all of the sequences need to have the same length. For those who are less, zeros. Yeah? That is actually the function that does it. The pre-processing sequence dot pad underscore sequences is what joins or pads all the sequences together. Again, don't remember the name of the function. It's going to be relevant next year, maybe. Okay? Things are changing, are evolving, even in programming, even within TensorFlow. That can change. In your mind, the key takeaway is sequences with different lengths need to be padded because they need to have the same length. That's all.
But just to understand that this max length here, this is the dimension of the matrix. You see now the shape, it will be 25,000 because we have 25,000 sentences in our data file that we loaded. And after that, we have specified that the maximum length, it will be equal to 200. So we are going to have 200 columns. So this is the shape now.
Exactly. And now, one good question would be why 200 and not 512 and not 1024? So the longer you make, that means the more input, the more tokens you include, right?
Yeah.
That could actually affect training a lot. That could slow down definitely the process. That will affect training a lot. And when we are doing sentiment analysis, again, we don't really need the full review to understand what's going on. And especially with RNNs that incorporate memory. Good? So we keep this number a little low, in the lower side, just to make sure that we are good with computational issues later on, okay, and training issues with backpropagation. So, therefore, after padding, we will still have 25,000 training points, training sentences, in a 200-dimensional space.
Just to clarify, because also I didn't say it correctly, let's say 25,000, these are reviews, not sentences, let's say, because sometimes we say sentences, but these are reviews. Each review can have more than one sentence itself. So it's only first review, second review, third review, and so on, okay? So these are reviews, because usually, I was explaining it that way,
Me too.
so it's as well. So we say sentences. No, it's not. Each review can have many sentences, as we saw the example.
Thanks. And technically, we should always say observations. But yeah, sentences, when Ogerta mentions, it could be a different application by itself. You can have a document and extract it into sentences and then do work with individual sentences as observations, if you want, okay? All right, so we are almost done because we have the setup here. We've got the sequences. We know that we are using 200 tokens. We know that we are using 25,000 observations or reviews. And we are printing the shapes, which are what they are. And now it's the time where we're going to do the modeling. Everything so far is smooth. We follow the protocol and we are ready. Yes?
Can you explain a little bit more about the truncation? Because does it just cut off at the 200 token, or is it some kind of selection process before that to kind of get some important words that are just taking the first 200?
So we are getting the first 200s. So within a review, right, we are getting the first 200 words. The rest will be discarded. So now it's your question about why 200 and not longer?
No, I was just asking whether we are selecting those 200 to be some kind of like more important words, keywords used in the review, rather than just the first 200, whatever they are.
So is it the first 200 or it will be the most important because they are sorted in the matrix by the frequency?
Here, I think it's the first 200.
The first 200.
I think. I understand now your point that do we discard the most important ones?
Yes, because maybe the most valuable part of the review that that should be important for the training might be.
That's a good point, and I can, you know what? I'm honest with you. I don't know right now. When I prepared this, I never thought about this, and I'm not sure what this does inside. So that's a great question, actually.
This that I'm saying about keeping the most important because the highest frequency they come on the top of the matrix. This happens during the back of work or
Okay.
the IDF, so it's like keeping the most important ones.
So that means
Process.
the 200 here is the most important ones?
I think so, but at least this is what we get from all this,
Yes. Okay, you know what you can do to try this out and test it out? Why don't you now go and grab one training sample from this and decode it and get the review?
If we ask Gemini, will it be able to tell us?
Yes.
It takes the last one.
It says that it takes the last. In my mind, that's what when I was writing this, I thought that it takes the last. But
Part. If you say 200 words, the last 200 words of your review.
But hold on, don't get confused with this.
If we
Just
have 500 words, it skips 300 in the beginning and takes the last one.
The way it's written.
but don't believe. Yes. But one thing. Okay, here is actually this is great discussion. This goes to reality now. We don't know, right? I don't remember. I don't know.
this is something for me it's not clear here where is the entity, or it is done because we are using existing data set. Because usually what happens, we have our own data set and we go through the whole pipeline ourselves. Maybe this is not the case because we are using existing
Yeah.
ones. So where is the entity here?
The what?
So where we compare
Ah.
to numerics?
there. And then there.
So, yeah, we didn't do it ourselves. That's
Yes.
what I'm saying.
Yeah.
That is why we.
But again, inspection is important, okay? Hold on. Don't ask Gemini, don't ask ChatGPT yet, all right? Do it yourself. We have pre-processed the data, right? We have them ready for modeling. Before we do modeling, let's do an inspection. Let's write one line of code that grabs one training observation, the first one, okay? Decode and get the review. See what it says, character by character, okay? Now, do the same before pre-processing. Okay, and see what it says. That will definitely solve your answer. It's 2 lines of code. Well, the first line you already have because we display. But the second one, you need to grab the one that we selected 200 tokens. Good? Okay, all of this matters, by the way, right? Because now if I don't get good results on my classification, that may be the case. That I haven't done a very good pre-processing, and I'm very glad that we have discovered this now. So we could improve just on this, on the pre-processing, okay? And it doesn't have to do with the model itself. All right, so here is the model, 4 lines of code. We are using an LSTM. I mean, you can use bidirectional if you want. This is an LSTM model, and we are going with the first layer, which is what Gerda pointed out, embeddings. Tokens need to be converted into matrices. That's going to be the input for the first layer. All right, so we are using 10,000 words. We are using output dimensions of 32. We are using the input length of max length. Okay, so all the different dimensions of the embeddings. And then we are start throwing the LSTM layer. Okay? The LSTM, we decided to have 32 features within that unit. Alright? So each word, each token now, in the embedded way, in the 2-dimensional array, gets into this state, incorporates something, loops back, next token gets in, loops back, this, that. Once this process is done within this layer, we go to the next layer, which is the classification. So we have an output, which is the age sub t, and we need only one neuron to make a decision, whether something is positive or negative. And we are using the activation function to be the sigmoid there. And after reading the summary and how many parameters we're going to use, 300,000 parameters, that's not bad at all. It's a light model. Okay. We are ready to compile. I have a lot of comments there, so you can go and read them, okay? We compile using our classical parameters, and then it's time to fit. I'm using 3 epochs, the batch size to be 64, then the validation split to be 20%, because we also need the validation piece from the training data, and you see the accuracy, how it evolves. 76, 90, 93, and it goes up. Good? So it really understands what the sentiment is about in the training data. Good? Questions? All right. Evaluating now the model means that we are taking a test data point that it never been part of the training phase. We give it to the trained model, we evaluate, and we get an accuracy of 85%, which is good, okay, in that case. We visualize a little bit the curves. Again, 3 epochs is not much, so you should go further down to see an overfitting. if there is one. Right now, it's nothing special there. You could say, you could claim that I'm safe, all right? And the training loss, same story, okay? Both are going down, and so on. You are making predictions. This function actually, this little piece of code, helper function, it takes one instance, which is one observation, makes the prediction, tells you what the predicted value is, tells you what the true value is, the true label is, and then they give you also something nice, the prediction score. The prediction is not in one sentence, in one observation, in one review. Okay, so I'm taking one whole review, I give it to the trained model. The trained model can tell me what the label is, and it can also tell me what the prediction score is.
Y and Y hat.
Exactly.
But this is just sentiments, ones and zeros.
All right, so we got the first review predicted correct, but with a low prediction score. However, the second one, the model is very certain that is a positive one, 97%. All right? Don't look at the output itself. It's not important, but look at the idea behind this. Once you are making predictions, now we should start thinking about interpretation. Okay, right now we are treating this as a black box, but it's time to unfold it and look inside. You see that you have a very low prediction score, right? So 0.07, 7%. While in the second one you have 97% certainty. This is where you should expect. Even starting at a small scale, even going to individual predictions, which is called local interpretability, you should start understanding what's going on within the prediction. Why does the model predict correct, but not with a high certainty? All right? What are the influential words that contribute most to the final decision? Are those relevant to the sentiment itself, or are those irrelevant? And the model is just making a prediction randomly, just flipping a coin. Good? Again, this has a name. It's called local explainability, local interpretation for each prediction. And there are tools to even inspect the most influential words within each prediction. And one that we're going to see in day 5, it's called the line, for example, the line model. Okay? Or the shape model. Okay? So, I think that.
Confidence?
Huh?
Is it how confident the model is?
Right.
Yeah. So this prediction is about the confidence of the model itself. And usually when we present the results of whatever models we deploy and so on, the next question is about how confident is. Because say, oh, we achieved an accuracy of 88% and this is very good and so on. And the next question is how confident you are. Okay? That's really important to answer.
Okay, so there are a couple mini challenges there for you to think about. Use a simple RNN for the same task. Use different number of input units instead of 32 make it 64 and so on. See what's going on, see what you get in accuracy. Do you improve? Do you increase overfitting? And so on. All of these are good things to think about. Also are good things to think about because the project is coming up. Okay, it's the same project. Now, the idea, by the way, before I start discussing the project, any questions about this? No? All right. Let's start with the project then, discussing the project. So, quick description. Now, what is the project about? We are talking translation, exactly. Not just translation, but it's a multi-aspect project. It has many different little aspects that you can get stuck with. So, at the end of the day, in this 5-day workshop, what we are dealing with is mainly classification. So binary or multi-label classification, if you wish. So multi-label means more than 2 labels, means than 10 labels, for example. And for the project, we decided to go with something called topic modeling. Okay? And topic modeling can be viewed also as a classification task. Topic modeling? Yes, I said topic modeling. Yes. As a classification task. And the idea is that each document has its own label, and we are trying to train a model in order for the model to predict the topic of the new document. Okay, so if you have labels as politics, sports, religion, and football, the idea is that you would like to train the model using training data and those labels, make decisions, and take unseen data points and see whether this new document, testing document, belongs to either one of those classes. Clear? So instead of binary, we do it multi-label, more than 2. Okay? Now, this is trivial. Okay, you can do it right now. But the idea here is to make it a little bit more challenging. So we decided to go with a data set that is not in English. You see that all of those here data are in English, right? So all of those NLP tasks, tokenization, stop word removal, lemmatization, stemming, blah, 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 are ideal for popular languages like English. Okay? Now we decided to go with an Albanian dataset, and those documents are written in Albanian and have been categorized in based on topics regarding those from the Albanian news. Okay, so there are documents about politics happening in Albania, and they have been classified as politics. Sports happening in Albania, categorized as sports, and so on. Now, if you're gonna train an RNN using just this Albanian dataset, would you receive the same accuracy in predicting the topic versus if I take this dataset, translate it into English, train a network, and make predictions? The first reaction is no, but which of the 2 languages is more powerful for informing your neural network to make such predictions? That is actually the question that we will attempt to answer in this project. So would the network be okay if we work directly with the Albanian language, or do we really need to translate all the observations to English and then train a new model just in English and see if we can make same predictions? Remember, translation is a difficult task, so you are adding a computational layer on this just to translate everything into English. That will actually kill your effort and computational power and so on. Is it worth to go through translation?
But
yes.
In order to compare, let's say, you have to keep the same structure for your networks, let's say, and we want to see about what is the impact of translating. At least this is how I see it. Yeah?
Mm-hmm.
So it's not. We don't want to see any impact that the network structure might have. We want to see the translation process if it's impacting the classification, because topic modeling is a classification. Let's group all the corpus of documents that we have, PDF files and so on, into different classes. It can be political, health, and different classes. But we want just to see the effect of translating.
And luckily there is a data set collected for that purpose. The data set contains thousands of Albanian news articles, and it includes also other useful information. As you see here, it has some publication date, publishers, sources, article text, and so on. Okay? Very nice attributes to use when you are going to do your interpretations. Okay? So in the workflow that we have suggested here, we are asking you to do several tasks, right? Starting with NLP tasks, hand-on, like normalizing text, tokenizing, and so on and so forth. Then translating Albanian articles into English articles using a particular API. If internet becomes an issue, we will figure this out. I have everything translated, but it needs some internet connection for that. And then define the classification task, which is, by the way, what we have done today. You can use an RNN for that. Okay? And then train and evaluate. Have two models, one Albanian, one English. Accuracy for the Albanian, accuracy for the English. And see what you get. Which one is higher? That's your first reaction. That's what you first need to do. Okay? Do we ask for too much? No, right? Okay, good. So that means that you can actually go and download the data and do that. Right? Yes. No, these articles, great. These articles are not translated. So the first challenge that you may face is not even into the translation.
I mean, here, the literacy inclusion issue. Should we have also translation from English? So there should be translation from the models, right?
Yes.
Yes. There is a data set, and in the data set that you will have, let's say it will be only Albanian articles there. So now you have to translate, and you will create a new data set where all the articles will be translated in English. And these articles in English now, they will be processed and they will feed in that LSTM that you will create, and you will get the output.
Very good. You are going fast. You are moving fast. But this is good. This is great. One of the challenges will be the impact of translation and whether which model you are using to translate, and how do you evaluate translation at the end of the day. All right? So I can tell you.
Sorry to interrupt. This might be the second question. Let's say the first question that we want to answer in this challenge is about if the translations impact the accuracy of the performance of it.
Yeah.
If it impacts, okay, and after that there is a second question that it goes further, what you are saying, and it makes sense, and it's a good point of view about how we can improve the translation, and also it will come up with an improvements in the classification.
This is not an easy project.
Yeah.
This is not a project that you do it as a homework for a class.
Yeah.
Okay? This is actually a very challenging project that may be executed within months, not one day. Now here, I mean, the reason why we give you this as a project is because we want you to start thinking about it. If you are interested, carry this over, build your portfolio using this project, and highlight it in your, I don't know, interviews or in your classes or in somewhere else. Okay? But this is actually very challenging. I tried to solve this project before, I mean, I assigned it without solving it. So, but I realized that the many challenges beginning. So challenge number one is that I downloaded the files, which are, by the way, 2 CSV files, and it doesn't even display anything because there are so many. It takes forever to display in the Excel file.
Download means downloading in our
Download
machine.
means download in your machine, yeah.
Locally.
Local. There is a CSV file in this link that we have that you need to download. You can work with technical, but try to download it just to see the challenge.
Yeah.
Okay? So, for that reason, what I did, I mean, I eventually downloaded it, but what I did,
So you can open from Excel, but you can
yeah.
no fancy plus.
So I just actually wrote a little bit of code to subsample articles and see at least how the data looks like. I mean, that was my main issue. And you can work from Kaggle, but I wanted to have it on my local machine, offline, no internet. And I want to see how it looks like.
You can do it in Python as well, so they just
Right.
important.
We wrote a little bit of code and downloaded this.
No, but they are missing some
They're missing a lot.
characters. You are getting wrong characters.
Could be.
No, it
It's
is.
because we have some special character
Yeah,
in
you
the
have
main, they
special
have to
characters.
replace or deal with that.
You are missing some of them.
Është karakteri ë që kemi në Shqipe këto, kështu që ka është kjo është
Okay,
pjesa e
very good.
You have two characters that are missing and then are being replaced with some
black.
special.
Yeah.
Challenge 2. Challenge 2. You are working with an Albanian language. So downloading is challenging. You are gonna miss special characters.
You just find and replace.
Yes.
You have to identify
Yes.
and you just do a find and replace function. Apply it.
What's the issue with that? The issue with that is that I do not know what are those characters. I don't speak Albanian, right? I'm not fluent in Albanian. So, I got this. Right? Okay, good.
Someone that speaks Albania can easily understand which are the
Yeah.
special characters that they are missing and where to replace them.
Very good. All right, now, challenge 3. Okay, I'm gonna tell you all the challenges before we go. Main categories. Do you like it more now? No, there are still a couple.
Yeah, they are still.
Main category. There are more than 10 content classes there. Okay, I think there are like 20, 30 classes. So topics. Okay, so what's the issue with that? The issue was that the class politics included most of the observations, while the class sports included less, while there were classes that included only one observation. Unbalanced. Can I do classification with this? No, you can't. So the challenge for you would be to actually balance the data set. Okay? Let me go.
Also in the outro you are missing like names. You see.
Yeah.
But you are not predicting the output. You keep whatever you have as in the content. You will not predict anything.
I translated, okay,
Translation is wrong.
and the translation is what it is. I don't know what it is, but I included one, I wrote the code, I translated, and I included one column in the file with the translation. Okay? So I go to this one. Bayern failed to beat Holstein Kiel in the penalty shootout, the one that took place in the German Cup, blah, 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 blah. Okay? Is the Albanian characters correct here?
No.
No?
No, you are missing.
But the translation was okay. By the way. You can just replace it, yeah. Yeah.
Even in the translation, in some names you still keep that.
Remember, you are doing topic modeling. You don't need everything there. Okay? Right. And again, I'm not showing you the solution here. I'm showing you what I did whole by myself. Okay? You do it. You do whatever you want, and you know better than me. But I got the translated content. All right? Do you want me to present another challenge? Yes. Huh? Okay. All right. Another challenge was, you see that I have a small.
Sorry. How did you do the translation? With Google Translate?
No. So very good. If you just go and do it line by line, it's gonna take you like 2 months to get the translation.
Next year, if we
Next
have
year
a
we're gonna be here and we're gonna have a translation. Yes. No. There is one 10 lines of code that you are calling an API, and you are actually giving the whole CSV file, and it gives you back the translations. So that is actually another challenge. Challenge number 4. When I do the translation, the Albanian text has 10,000 tokens, but the translated output is only 512 tokens. So what? So this is a challenge. Why is that? Because the API that I called does not allow me to translate more than 512 tokens.
It's a limitation, a constraint.
There is a limitation. Why is that? I have to pay a little bit to get more than 512 tokens. I don't want to pay. So I just stayed with 512 tokens. Does this gonna affect your finance? Yes. Okay. Challenge number 5, and we are done. And there are more, by the way, but I'm gonna stop at 5. I don't have it. I don't present it as a CSV file, but I can tell you what the challenge was. The deep neural networks didn't perform well. Okay, so be ready to actually accept something very low in performance. All right, but sorry, what performed really well was logistic regression.
Traditional
Traditional
learning
stuff.
now.
Traditional stuff. Okay, let's go back to tradition then. For that.
And let's think about why. This is the big question. It's not just one run and you see that it's performing better, but we have to figure out why it's better than these complex neural networks that we are spending so much time to understand and run and so on.
That doesn't mean that neural networks are bad, right? But when we are working on something, we have to think outside of the box, not what is the hype. Okay, so we have to think about other stuff as well that we have learned in our careers and probably use it. Good. Enjoy.
It's not easy.